Getting back to benthic communities, just poorly planned slide sequence in this case, we could trace how diversity, this axis shows the biodiversity versus water depth and log scale. Diversity peaks just before the ice covering is on the peak, then it drops down, then it increases again with water depth as the dynamic disturbance pressure is released. Moving closer to home, Fundy, it was multi-beamed for about 4 years, since 2009, I believe, with some patches multi-beamed in 2004 or 90s, late 90s. How do we deal with remote sensing information? So yes, we run multiple surveys, we stitch all the data together, we ground truth it at, say, a number of locations, and then we try to, again, establish the process or interpret the process. In this case, these are sand dunes, and this is a very fancy pattern, almost an alien pattern, which shows interference of water flow, almost like interference of light. Very similar process. This is very valuable for hydrographic modelers. Now, another slide created by my colleague Russ Parrott shows 94 to 2007 comparison of the same place using different technologies but brought to kind of common denominator, which shows how mobile these features are on seabed. And if you look at, for example, this little sand dune, you can see how it's moving in 10 years, okay? And the yellow bars are about 50 meters long. And same applies to these ones here. And again, if you look carefully, you'll see that the bottom ones are moving in one direction and the upper ones are moving in a different direction. And this is all affected by the flow. Okay, ground truthing. So we have a number of tools, famous CamPod and all kinds of grabs, and we collect all the data. It's all going to the huge database. And it's all well described. Oh, jeez. Okay, and just 5 minutes? I don't believe it. I started 10 minutes later. No. I started at 16 minutes past. That's why I took it. At lunchtime. So we can accurately geoposition, geolocate every sample on the seabed, and basically go through every image and zoom into it. So every image is rotated and located on the seabed and interpreted in terms of its biology and sediment, and again used for interpreting the morphology and habitats in general. In this case, this is a snapshot of Fundy horse mussel reefs, famous structures which are up to 3 kilometers long and about 30 meters wide and about 6 meters tall. Some of these ridges. So these are all not really reefs. These are accumulations of sediment which are armored by modulus, by horse mussel. And they all flow parallel, which is in contrast to the actual moraines and sand dunes, which are mobile in this case. Okay, scrolling through really quickly. So putting this together is a challenge, and it's a matter of argument between ecologists and geologists and people who see things a different way. Different mappers produce different maps, and then we're trying to put this into a system. So what do you do with remote sensing data and physical samples, and how do you merge all these things together? So basically, if you choose just one way to achieve, let's say, benthic habitat map, or one way to achieve sufficient geology map, it will be infinitely incomplete, and it will have it will include a number of huge assumptions of how you do things. Each red circle says this is a critical point where you assume things, and if your assumptions are wrong, your map is wrong. And in this case, achieving this map of seascapes, it's a made-up word, which is kind of in between geomorphology and habitats, done by my colleagues John Shaw and Brian Todd. It brings us kind of part way through this chart through merging physical, optical, and acoustic samples together and saying, okay, these big red areas are areas where you find mussel biofilms, these are deep muddy basins, and so forth, and actively migrating bed forms. this map is infinitely useful to marine managers, to managers of fisheries, to managers, to people who are planning to put underwater infrastructure, such as tidal turbines. You know, they're looking for bedrock. This is an example of nice, stable piece of seabed where putting infrastructure is possible. As a system, you know, all these snapshots, you know, can be systematized, you know, in the way which is realistic. And, you know, in real environment, we have constraints such as, you know, personnel, financial constraints, time constraints, you know, which tells us, you know, what we can actually do. We have, you know, 1 month and no people to do this. We can do some kind of broad scale, arbitrarily map. You know, if we have, you know, 5 years and then have, you know, $50 million, well, that's a different approach. And so, you know, in this kind of fully free, you know, idealistic environment, we can carry full geophysical and ground truthing sampling and produce maps which would be useful for resource management, MPA design, environmental assessment. So this is high resolution remote sensing plus sampling approach. In the other opposite end of the spectrum, regional plans, LOMA design, integrated management plans for broad areas when you have more constraints. So where are we now? When people talk about mapping at Geological Survey of Canada, they mostly think about this type of mapping. This is the UNCLOS project, which was really well financed. So last, let's say, 5 years, most of the mapping was this. It wasn't the previous slides that I described. It was all done 10 years ago. This is what mapping is now. This is all offshore, multi-beam and seismic surveys, 13,000 kilometers mapped, you know, in the Atlantic, 15,000 kilometers in the Arctic. A lot of work, a lot of people, a lot of money, mostly for establishing the foot of the slope and extending our economical zone. And it's a great international achievement. Okay, doesn't relate really closely to coastal mapping, but it uses a number of technologies such as AUVs, $200,000 a pop, and so forth. But we're trying to bring mapping closer to shore again, closer to integrated ocean management again. And 2 years ago in Galway, European Union, Canada, and the United States have signed a Galway agreement. So it was signed at a very high ministerial level, agreeing that three regions will collaborate in studying North Atlantic. And the collaboration will be in 3 areas: ocean monitoring, seabed mapping, and ocean literacy, promoting knowledge of the oceans, basically, to everybody who cares and actually trying to bring the interest up. And within this, there is a group, within this initiative, there's an Atlantic Seabed Mapping Working Group, and we are the part of this. So Geological Survey of Canada is part of this. We proposed that 2 years ago in Galway, and it happened. So there is a lot of money being put by European Union in ocean mapping at the moment. A lot of Canadian private companies can engage in this and get funded, partially through this process. But most importantly, the federal government is again interested in doing this in integration with other agencies and with other countries. And it's about time to do this. I still have 5 minutes. I'm not a control freak, by the way. So the issue, you know, I could have started with a slide or ended with a slide, but the issue is that we have navigational charts of good quality for about 60% of Canadian offshore, just judging on the time and the frequency of the update. Required frequency of the update. It's a kind of round, pretty much arbitrary figure, but it's close. Multi-beam mapping covered about 10% of Canadian offshore. And geological maps at the scale that I have shown, at 1 to 50,000 scale, less than 5%. Benthic habitat less than 1, because it's a pretty new discipline in general. So how can we manage offshore if we have so little knowledge? You know, in Google Maps, you can open up, you know, Street View and look at your cat in the window. You know, in the ocean, it doesn't happen, right? So this is the multi-beam data NRCan currently hosts. This is all the information we have at the moment. The Arctic part of UNCLOS is not shown because it's classified, but you know, that seems like a lot. It just seems like a lot. You just look at the areas which matter the most, the shelf areas. Everything shown within 200 meters. It's all blank. This is part of the UNCLOS Atlantic claim. And again, these stripes look wider than they actually are. And these are the locations of the maps, of the A-series maps that we have published already in geology. Huge seabed. Arctic is a very, very challenging environment for mapping. We need significant investment in ships. We need ships to map. We need to store the data somewhere. We need to integrate departments, regional, federal, everything together, and basically coordinate work, as much as we can. For about 2 years, we were talking about targeted ocean mapping strategy, that federal level strategy for the benefit of Canada in general, on the one visit, many measurements principle. Let's use the ship for doing geochemistry and mapping and trolling and benthic sampling, whatever, while it's still there. And when we were writing this justification, we actually were thinking, how can we justify it to the current minister, who was the banker? The only justification that would be accepted was the return on investment. So if we look at other countries, Ireland had 6-to-1 return on investment in ocean mapping. They have mapped their offshore in about EZ in, I believe, in 4 years. And they were visiting us 20 years ago to learn how to do this. States is claiming that coastal mapping has 31-to-1 return on investment. That's fantastic. That's just incredible. Of course, all these numbers are coming from private, consulting company reports, and they may or may not be true. But the benefit is definite, and it's hard to argue with it. So I'm wrapping up, and these are the benefits: safety, security, environment, infrastructure, food supply, energy and minerals. Everything I started from is there, hidden in the ocean mapping. Thank you.